Okay, so this is going to be a short video on igneous rocks for part of the rock and roll project. We're going to talk about igneous rocks, what they are, how they are made, how we can figure out how old they are, some clues on how we can identify them, and some of their basic characteristics. Okay, so again, igneous rocks, let's look first at their formation. So igneous rocks form from either magma or lava. Okay, so if we're looking at magma or lava, we're going to look at, what is the difference between those. Magma is below ground, is our main difference, and lava is above ground. Okay, so they're basically the same thing, and if this is our ground, where anything that we're talking about down here is going to be magma, and anything once it comes up onto the surface, so we may have some magma below ground, but as soon as it becomes above ground and at a volcano, or as most of these pictures are, it becomes lava. Okay, so that's a minor distinction, but it also has an effect on our rocks, because the main thing that it does is it determines how quickly they cool, and that determines a lot of the characteristics of our igneous rocks. So first thing that we want to do, kind of some definition words, is magma is anything that is below ground, and lava is anything that is above ground. Okay, and that's a good distinction that we'll need to know. Okay, so if we are then looking at our next slide, we're going to talk about crystal size. And we've got a few diagrams in here. If we are looking over here, we're looking at various different crystals inside of this rock. And we have large crystals here, and we've got much smaller crystals here. Okay, and that's a major distinction between igneous rocks. Some have very small crystals, even no crystals, depending on how quickly they cool, and some have large crystals. So we got a few examples. We can see here each of these points is a crystal, and often we can see different colors as crystal sizes. So those igneous rocks are made up of a bunch of crystals, and that's magma or lava that has cooled. So generally what we see is that magma, when it's underground, so magma is underground, magma cools, excuse me, magma cools more slowly. Okay? And if we think of crystals as needing to grow, because crystals develop over time, magma, since they're cooling slowly, those crystals have more time to grow, so magma has large crystals. Okay? And so conversely to that, if we're talking about lava, and lava is above ground and it's exposed to the air, we can think of the ground as being like a blanket. You cool off slower underground, under a blanket. When that magma is underground, it cools slowly. If you were to take that blanket off, you would cool more quickly. So lava cools quickly, and therefore our crystals have less time to form, and so they have small or no crystals. Okay, so depending on how fast our magma or our lava cools determines the size of our crystals. Okay, so again, slow cooling magma has large crystals, fast cooling lava has small crystals. Okay, that's our main thing that we're looking for here. So again, we've got two main types, and it follows this same pattern that we've talked about. We've talked about intrusive and extrusive. Again, they follow the same characteristics that we've talked about before. Intrusive, so as it says here, intrusive, these form below ground. Okay, so up here on this diagram, gonna kind of highlight examples of underground magma. Okay, it's underground. It's going to be slow cooling. It's going to be coarse grains. It's going to have large crystals, and we call it intrusive. Okay, cooling slowly. The other type, as you can see from these diagrams, we call it extrusive. You can think of an exit or being external. Those are things that cool above ground. Okay, and that is extrusive. That's lava. All of those things, and those are examples of volcanoes, islands like Hawaii where the magma spills out into the ocean. Those are all extrusive examples of lava. Okay, we also can have a few other examples. Back to the intrusive, these veins that we have, those are also considered intrusive. Okay. All right, so we've labeled all of those. We've got several examples. We've got intrusive, which is below ground, which is therefore our magma, which therefore cools slowly and has large crystals. The other example is we have extrusive lava, which cools quickly. It's above ground. It's got small or no crystals. And these are examples down here. So again, our intrusive, we've got large crystals, and we consider them large if we can really identify them with our eyes. And if we can see these different colors, they can be various different shapes, but basically if we can see them with our naked eye, we consider them to be large crystals or coarse grained. Our extrusive ones, our fine grained or our small grained ones, this is a rock known as Obsidian. It actually has no crystals, and it's one of the fastest cooling or the fastest cooling igneous rock. It basically is glass. We can't see any crystal size in them. Here's an example of one that is flowing lava. It is small crystals, but again, they're not of the size that we can see with our naked eye. So they are small crystals, extrusive, formed from lava, and above ground. All right, if we progress to our next slide, we can look at determining the age of our rocks. So throughout this project and throughout this unit, we're going to be talking about how can we figure out how old these rocks are. And what we're looking at here is going to be talking about our absolute or radiometric dating. And that has to deal with the atoms that are actually inside these rocks. And igneous rocks are unique in that they allow us to, primarily are the only rock that allow us to determine the actual age of that rock. Our other types of rocks are sedimentary and are metamorphic. Because of how they're formed, we can't figure out exactly when that metamorphic rock formed or exactly when that sedimentary rock formed, partly because of how they're made. Okay. When we talk about igneous rocks, as it says here, when the magma or lava cools, it's similar to resetting the radiometric clock of the rock. And what we mean by that is if we look at this example over here, we've basically got a rock as it's going through time. Okay, each of these is an example of the rock at different times in its life, we could say. At the beginning, right as the rock crystallizes or cools off from magma or lava, it has 100% of a radioactive material. Okay, so the rock is not entirely made up of radioactive material, but it does have some atoms in it that are radioactive. Okay, one example, and the example that's here, is uranium. There are many other examples that you'll gain experience with throughout this unit, but at the moment that it cools, all of the radioactive elements are what we call a parent element. So we use percentages of parents to daughter atoms to determine the age of the rock. So basically what we have, if we've got this uranium atom, okay, we're going to say this is our uranium atom, this is our parent, that's what it starts at, and eventually it will become a daughter. Okay, so it becomes a daughter, which is a different type of atom. Okay, this one should eventually become lead, but its first step will be something else, that it will become its daughter. And if we look at uranium atoms of this particular type of uranium, they have what we call a half-life. Now what that means is if we had, say we have 100 atoms, uranium atoms to start out. Okay, so we're starting with 100 uranium atoms, and these atoms will, at random times, they will randomly change into the daughter atom. Okay, so they randomly change into the daughter atom. So if we are watching one individual atom, we can't predict when that one individual atom will change into the daughter. Okay, but if we're looking at a large number of those atoms, and a large number would generally be more than 100, but 100 is an easy number for us to work with, we can watch for what we call the half-life, and that's the amount of time it takes for half, so in this case 50 of those atoms, to become daughter atoms. Okay, so we have 50 atoms of uranium now, and at some point 50 of them have changed. Okay, so 50 of them at some point have become daughters. Okay, so that process, again, just to take a moment, of them becoming parents and becoming daughters is not a magical process. It happens in natural ways. The atom may give up some protons or neutrons from its nucleus, or it may just give up a proton, or it gives off a gamma ray and splits into different elements. Okay, and they become other elements, and so that happens in predictable ways. If we have this particular type of uranium, we know how it's going to become and which daughter atom it's going to become. Okay, but if we look at one particular atom, we don't know when that's going to happen. But if we are looking at a large number, we have what's called this half-life. Okay, and a half-life is the amount of time it would take for half of them to become the daughter atom. Okay, so in this case, the half-life is a specific amount of time. In this one, in our diagram over here, that happens to be 1 billion years. Okay, and so if we come upon this atom, let's take a hypothetical situation. We've got 100 of these uranium atoms. We sit there and we let them sit there, and we come back a billion years later. We would expect to find only 50 of the uraniums, but also 50 of the daughters. Okay, so we're using that relationship of the numbers of uranium parents to the numbers of daughters that we have, and we use that percentage to figure that out. So if we look here at our diagram, in this first step, we went from all of them being the parent, and now half of them, in our case 50, are the daughter, and then we know that the half-life is 1 billion years. So if we see that percentage of half parents and half daughters, we know that it's been 1 billion years since this cooled off and crystallized. Okay, if we go another half-life, half of those 50 that are left will have then become daughters. Okay, so basically what we're looking at here is we've essentially got 25 parents and 75 daughters. Okay, so we've got 25% here and 75% here. Okay, at that instance, we then know that 2 half-lives have gone by, and we know if a half-life is 1 billion years long, that rock is now 2 billion years old. And in this final situation that we're looking at, again, those 25 parents, half of those would be gone. So this gets us to a weird number where we get 12.5 atoms. So we can't have a half atom. So we're about 12.5% have parents, and the other atoms are now have become daughters. Okay, so at this point we are looking at 87.5% are now daughters. Okay, so again, if we come upon a rock and we look at it and we know that we see these uraniums and we see these daughters, and we know that we've got 12 and a half, a ratio of 12.5% are parents, the parent uranium, and 87.5% of them are daughters. We know that it's been about 3 half-lives, and if we know that a half-life is 1 billion years, we know that it's basically 3 billion years old. Okay, and that's what we see here on this graph. Is as half-lives go on across here on the bottom, the 1s, 2s, 3s, and 4s, we can predict what the percentages of parents to daughters should be, and we use that percentage to determine how old a rock is. Okay, and we'll get lots and lots of practice with this, but that is the basic overview of how we can figure out how old igneous rocks are. And again, that was only true for igneous rocks. It's much more difficult to determine the exact age using radiometric dating for sedimentary and metamorphic rocks. We have to use what we call bracketing, and that's what we'll focus on in our class. And other videos for those two things, for types of rocks, for metamorphic and sedimentary, we'll discuss that. Okay, so these are just some skills for identifying types of rocks. You've got basically some different characteristics that we're going to look at. We're going to look at small crystals. We're going to look at large crystals. So this one we're looking at is small crystals right now. We're also going to look at a light colored rock and a dark colored rock, and we're going to begin to practice some of these skills. So first thing, when we look at smaller crystals, this is what we call rhyolite, and these crystals, especially where it's red in color, are a lot smaller. Okay, and here when we look at this basalt, which is the name of this rock, we can still see these very, very small light gray or dark gray or black different dots, basically very small on this rock, but those are all crystals. Okay, so we've got two examples. Again, we're using those crystals and the crystal sizes to help us to identify those rocks. Our next one that we're looking at is large crystals, and these are probably the easiest igneous rocks to identify because the crystals are so large and so easy to see. And again, we've got an example of a light colored one and a dark colored one. This is granite, one of our most common rocks that we will see as far as igneous, or one of the easiest ones for us to identify. It's got large crystals. We can easily see them and distinguish them from others. Same with our gabbro over here. Large crystals and easy to identify. Okay, another igneous rock that we often have, since we are dealing with lava in this case, they sometimes get holes in them, and those holes are when the lava is foamy, or it's extrusive, it's on the surface, it has air bubbles in it, is what those are. And two examples, a light colored one and a dark colored one, is pumice, and we can see those air holes there, and scoria, which is often a rock that ends up in gardens or decorative gardens that we can see as scoria. So those holes are an easy way to identify a rock as igneous. That's the only rocks that have those holes, because they are actually air holes in that lava, that liquid lava, and so those are easy to identify. And again, we've got a light and a dark example that's there. And our last one, one of probably the easiest igneous rock to identify, is obsidian. Again, it has no crystals because it's cooled very, very fast, and it's just basically a piece of glass that we have. Obsidian, it's been used to make arrowheads or lots of other tools, and that's commonly where we'll think of obsidian. It's usually this black, sometimes a dark green color, can have different shades, but it generally looks similar. Basically just a chunk of glass that is a rock. We only have a dark example here. There isn't really a light colored example to provide you there. Okay, so that's a great overview of igneous rocks. We've covered general things like how they are formed, how we can identify them through crystal sizes. We've talked about them: lava, magma, extrusive and intrusive, and also how to date igneous rocks using the atoms, percentages of atoms inside of them, parents and daughters. And we've also discussed some basic identification of some simple or common igneous rocks.